Hello everyone. Today I am going to discuss a very important topic of soil mechanics, that is grain size distribution of soil. So basically this grain size distribution of soil can also be termed as grain size analysis or particle size analysis or grain size analysis, whatever it may be. So this grain size analysis we require because whenever we are collecting any soil sample from the field, that time it's a chunk wherever lots of particles are there of different sizes. Because we require this analysis, the particle size analysis or grain size analysis, because we have to know what kind of particles of different diameters are present in the mass and it is of how much percentage. Because the soil characteristics or soil behavior basically it depends on particle sizes. That's why we require this grain size analysis or grain size distribution. Now there are different kind of methods to do this analysis. First of all, the soil particles that are available on our earth surface, that may be classified in two categories depending upon its particle size. One is your coarse grain soil, another one is your fine grain soil. This coarse grain soil may also be termed as cohesion-less soil. Now what is cohesion? Cohesion means the particle to particle attraction force. So in coarse grain soil there is no particle to particle attraction force, that's why it is called as the cohesion-less soil. And another type is fine grain soil, wherever particles are very fine, and it is also may be called as the cohesive soil. Means there are particle to particle attraction force is present in the soil mass. So from this chart it can be seen that the soil can be classified in two categories, coarse grain soil and fine grain soil. Now under coarse grain soil there are two types of soil mass, that is gravel and sand. And under fine grain category, soil mass is your silt and clay. So clay have the finest particle size. From this table, it is depicting the typical particle size of different kind of soil particles. The largest particles is your boulder. It have the diameter more than 80 millimeter. Then comes as the gravel, which have the particle size from 4.75 mm to 80 mm. Next come sand, which have the particle size from 75 micron to 4.75 micron. Then silt have the particle size from 2 micron to 75 micron, and clay have the finest particle size, which is less than 2 micron. You know, micron, 1 micron is equal to 10 to the power minus 3 millimeter. Now sand again can be classified in three categories, means there are three types of sand. One is coarse sand, which have particle size 2 millimeter to 4.75 millimeter. Medium sand have the particle size from 425 micron to 2 millimeter, and fine sand have 75 micron to 425 micron. Now comes as the method of grain size analysis or grain size distribution. Basically there are two methods. One is your sieve analysis, which is also be called as the dry analysis. Another one is hydrometer analysis or weight analysis. First comes as sieve analysis. This sieve analysis can only be done for the coarse grain soil which have the particle size more than 75 micron. Because in soil earth, the lowest aperture size sieve that we use is 75 micron. So there is an Indian standard sieve set that we have to use, having aperture sizes starting from 80 millimeter, then 40 millimeter, 20 millimeter, 10 millimeter, 4.75 millimeter, 2.36 mm, 1.18 mm, 600 micron, 300 micron, 150 micron, and 75 micron. And the last is the pan, which is actually a collection pot, means the soil mass that will pass through 75 micron will be collected in the pan. So these different sieves have to be arranged in a descending order. That means higher sizes will be at the top and finer sizes will be at the bottom. So in this slide, the sequence have been mentioned starting from 80 millimeter to 75 micron. After arranging in a descending order, what we have to do? We have to take a particular amount of soil mass that is to be placed at the topmost sieve and it will be covered by a lid. Then we have to shake it either by manually or mechanically. Generally we use mechanical sieve shaker for the sieving purpose. So after sieving, we have to segregate each and every sieve. Then we have to take the weight of each sieve including the soil mass. So from that we can find out how much the soil mass retained on particular sieve or on each sieve. So this is the set or the schematic diagram wherever the sieves have been arranged and it is being shaken in a mechanical sieve shaker. After sieving, we have to go for these following calculations. First, we have to find out percentage retained. Already we have determined the weight retained or mass retained on each sieve. Then we have to calculate the percent retained of soil mass on each sieve. That can be calculated by mass of soil retained on each sieve divided by the total mass of soil taken for the sieve analysis multiplied by 100%. Then we have to calculate the cumulative percentage retained on each sieve. That is equal to the sum of percentages retained on old or coarser sieves. Last of all, we have to find out the percentage finer than any sieve. That will be equal to 100 minus cumulative percent. So, from this data, we are getting the particle size which is equal to the sieve size. The soil mass that is retained on the particular sieve, that is the sieve's particle size or the sieve size of this soil mass. From this calculation, we are getting the percentage finer. Now, these two data means the particle size and the percentage finer. This resulting data will be presented on a semi-log paper. And from there, we have to draw a distribution curve. When we are plotting it on the semi-log paper, we have to plot particle size or the grain size along x-axis, which is in a log scale, and percentage finer along y-axis, which is the arithmetic scale. After plotting it, this kind of curve, the graph we will get. Here along x-axis particle size have been plotted in log scale, and along y-axis percentage finer in arithmetic scale have been plotted. So this curve that has been drawn, this curve is called as the grain size distribution curve. But if we take the scale along x-axis in ascending order, that time the graph will be opposite. That means it will looks like S. Here, in this graph, the picture, the scale has been taken along x-axis in the descending order, starting from 10 mm to 0.01 mm. But if we plot it in ascending order, that time it will be started from 0.01 to 10 mm. Then the shape of the curve will be like this, like S. So this curve is called as the grain size distribution curve or GSD curve, and it looks like S. That's why it is also being called as the S curve. Now comes as hydrometer analysis or the weight analysis. Here the soil mass that will be used, that is the soil mass that have been collected in the pan. After sieving, the soil mass that have been taken in the pan, it have the particle size less than 75 micron. It is less than 75 micron. So that cannot be analyzed by sieve. We have to go for the hydrometer analysis. Here we have to prepare a soil suspension by taking soil of 50 gram, in this soil suspension, we have to use a dispersing agent named as sodium hexametaphosphate, which will be dissolved in water, and by adding more water we have to prepare a soil suspension of 1000 ml or 1 liter. In this slide, it has been shown the schematic diagram or the schematic arrangement for hydrometer analysis. This is the hydrometer. It is made of glass. This is the bulb part of hydrometer, and this is the stem part. After preparing the soil suspension, which including dispersing agent, dust soil sample of 50 gram, which have the particle size less than 75 micron, and water. This suspension will be placed in a jar or measuring cylinder made of glass, obviously. Then we have to shake it properly. Then we have to immerse the hydrometer. Obviously, before immersing the hydrometer, you have to calibrate it. That means we have to establish a relationship between the effective depth and the hydrometer reading. Effective depth means whenever we are immersing the hydrometer in the measuring cylinder, where the soil suspension meets the stem, from that point to the center of the bulb, this is called as the effective depth. And where the suspension is touching the stem, that is the hydrometer reading. So we have to calibrate the hydrometer, means we have to establish a relationship in between hydrometer reading and the effective depth. Now after immersing the hydrometer, when the time will elapse, we have to record the hydrometer reading. In a time interval of 15 seconds, 30 seconds, 1 minute, 2 minutes, 4 minutes, 8 minutes, 15 minutes, 30 minutes, 1 hour, 2 hour, 4 hour, 8 hour, 24 hour. In this time interval, we have to take the hydrometer reading. So it is obviously can be said that at the initial time, when the soil suspension was in a uniform concentration, that time the hydrometer will immerse less. But when time elapses, the soil particles in the suspension have the tendency to settle down. So in the bottom portion of the measuring cylinder, the concentration will be more, and in the upper part of the measuring cylinder, the concentration will be light. So when time will elapse, particles will settle more, so obviously the hydrometer also will immerse more. So it will give you the hydrometer reading. Now from this reading, we have to go for the further calculations. Whenever the soil particles in the suspension is settling, that time is following the Stokes law. That means the velocity of particles, when it settles down, it follows the Stokes law. So according to Stokes law, the terminal velocity of any particle in the fluid will be given by this expression: V is equal to gamma S minus gamma W by 18 mu into d square. Here V is the terminal velocity, gamma S is the unit weight of soil solids, gamma W is the unit weight of liquid with the water, mu is the absolute viscosity of the suspension, and d is the diameter of the sphere of the particle. So from this expression, V can be calculated by following the formula L by D. Means how much length it is, or the distance is traveling with respect to how much time. So with respect to each time, elapsed time that we have recorded, the different velocity will be calculated. Gamma S and gamma W, it is all known to us, as well as the viscosity of the suspension can also be calculated. So only unknown parameter in this expression is the diameter of the particle or the particle size. After replacing all the expressions of V, the diameter of particle D can be calculated by this formula. After getting the hydrometer reading during the experiment, 3 corrections have to be applied on the recorded hydrometer reading: meniscus correction, temperature correction, and dispersing agent correction. Meniscus correction, the hydrometer that is made of glass. So when the suspension level is touching the stem, that time a meniscus formed. As your suspension is a heavy suspension, you cannot look inside the suspension. That means you cannot take the reading of the hydrometer by viewing inside the suspension. You have to take the upper meniscus. But the actual reading will be given by the lower meniscus. That's why we have to apply the meniscus correction, which is positive. Then comes temperature correction. This correction is to be applied with respect to a standard temperature of 20 degrees centigrade. The suspension that we are using, what temperature it consists at that time. If it is more than 20 degree, correction will be positive. If the suspension temperature is less than 20 degree, correction amount will be negative. Then comes as the dispersing agent. The dispersing agent correction, it is to be applied because, as I have told earlier, that during hydrometer analysis we have to add a dispersing agent, namely sodium hexametaphosphate. So whenever, what is the function of this dispersing agent? It will disperse the particles. As the particles are very fine, in presence of water, it coagulates. That means lots of particles get together and form a heavier particle. If we don't add this dispersing agent, this heavier particle will settle down fastly. But our target or objective is to make the suspension in such a way so that each and every solid particles will settle down individually. That's why we have to add this dispersing agent. It will disperse the particles, so it cannot coagulate with each other. So it will be settled down due to its self-weight. So whenever we are adding this dispersing agent with the solution, obviously it is an impurity. That means the specific gravity of the suspension is increasing. we have to apply this dispersing agent correction, which is negative. So, finally, to get the corrected hydrometer reading, we have to apply the corrections. So that is equal to RH, the hydrometer reading that we have recorded, plus Cm means the meniscus correction, plus minus Ct depending upon the temperature of suspension. If it is more than 20 degree centigrade, it will be plus, positive. If it is less than 20 degree centigrade, it will be negative. Minus Cd means dispersing agent correction. So after getting this corrected hydrometer reading, now we have to calculate the percentage failure, which is given by G or Gs divided by Gs minus 1 into Rc by Ws into 100%. Here G or Gs is the specific gravity of soil particles, Rc is the corrected hydrometer reading, and Ws is the weight of soil grains that we have taken in the soil solution suspension, that is equal to 50 gram. So now this particle size that we have calculated in the earlier slide and the percentage failure that we are calculating from this slide to be plotted now on a semi-log graph paper in a similar way, and the GSD curve will be drawn. So this is the grain size distribution curve, a typical grain size distribution curve. Here your scale along x-axis have been taken in a ascending order, and percentage failure along y-axis. So this S type of curve we are getting. This curve is called as the GSD curve. Also it can be termed as grading curve. So from this complete grain size distribution curve or the GSD curve, the following informations can be obtained. First is the grading characteristics, which indicate the uniformity and range in grain size distribution. And next one is the percentage or the fractions of gravel, sand, silt and clay. That means in the soil mass, how much clay is there, how much silt is there, how much sand is there, how much gravel is there, that can also be found out. The grading characteristics of the soil mass that we are getting from this GSD curve, from the shape or the nature of the curve, we can determine what is the type of soil or what grading it consists. The grading characteristics can be categorized in two ways. First one is the uniformly graded or poorly graded soil. That means wherever this curve representing the nearly vertical lines as shown by the curve. A such soil possesses the particles of almost same size. That means in the soil mass, all the particles having similar size. Or in other words, we can say other sizes of particle are absent. And next one is the well graded. That means gradation is very good. So this can be represented by the curve possesses a wide range of particles starting from gravel to clay. That means here all type of particles are present in the well graded soil. But in poorly graded or uniformly graded, similar kind of particles are present, or we can say other type of particles are absent. grading curve or the GSD curve. Now we can find out three important points, that is D10, D30 and D60. D10 is the size of particle corresponding to 10% finer. That means from this grading curve or GSD curve, we will draw a horizontal line from 10% finer from y-axis. Where this line touching the curve from that point, we are drawing the vertical line. So at x-axis the diameter that we are getting, that is your D10. So similarly, we are getting D30 and D60. This is the size of or the diameter of particles corresponding to 10% finer, 30% finer and 60% finer. So from these three values, now we are determining, first is effective size, which is given by D10. The D10 value is called as the effective size of soil or the soil mass that you have taken for the analysis. Second one is the uniformity coefficient, that is CU, that is equal to D60 by D10. Next parameter, curvature coefficient, CC, that is equal to D30 square divided by D60 into D10. So from these two-dimensional parameters, that is CU and CC, we can make comment that which type of soil it is. If the CC value, that means curvature coefficient value, if it is lies in the range of 1 to 3, the soil mass is called as the well graded soil. That is, the grading of soil is very good. If it is the CC value is beyond value of 3, or if it is less than 1, it will be your uniformly graded or poorly graded soil. So in this way, from CC value and CU value, we can make comment on the type of soil. Thank you. Thank you very much.